Question number 5. CCl4 is an effective fire extinguisher and is no longer used because of its toxicity and its role in the depletion of the ozone layer. So depletion means to remove the ozone layer. Ozone is a form of oxygen. Instead of being O2, it's O3. In the upper atmosphere, a bond in the CCl4, well, that's carbon surrounded by 4 Cl atoms, bonded to 4 Cl atoms, so the bond that's broken must be a carbon to chlorine, breaks and the reactive species are formed. A reactive species that's formed in this case is called a radical. Identify the condition that causes a bond in CCl4, we know that's a C to Cl, to break in the upper atmosphere. Deduce an equation for the formation of the reactive species. Well, first of all, in the upper atmosphere, what happens is you get ultraviolet light from the sun, and that's the energy that's needed. The ultraviolet light provides the energy to break the bond. UV light. The equation, well, the CCl4, what actually happens is, in CCl4, one of the bonds between the C and the Cl breaks, and there's a pair of electrons in that bond that's forming a covalent bond. And actually, what happens is, between the C and the Cl, just one of the C to Cl's, the pair of electrons separate, and one electron goes onto the Cl as the bond breaks, and the other electron goes onto the C. Now that's come from the Mark scheme. I've taken that from the Mark scheme, but that dot, that unbonded electron, that's what it is, has come from a bond between the C and the Cl, a covalent bond, a shared pair of electrons, and that's actually gone back onto the C. We know it's gone back onto the C because the C has got 3 Cl's bonded to it, 3 chlorines bonded to it, and it should have 4 bonds. So that electron is on the C to make up for the fact that it's short of a bond. That unbonded electron on the Cl and on this radical as well makes both of these very reactive. One of the reactive species from CCl4 is this one, acts as a catalyst. It means it's going to be reformed in the decomposition, that's the breakdown of ozone. Write the 2 equations to show how the species acts as a catalyst. Well, first of all, we need this, Cl dot, that's the reactive species, and it's going to break down ozone. Now ozone's O3. Now there's only 2 forms of oxygen, O3 and O2, so it must make O2. The Cl dot, the chlorine radical here that's made the reactive species, reacts with O3, ozone, and the only thing it can make, the only other form of oxygen that there is O2. So O3 automatically forms O2. And then you can work out what's left. What haven't we used? Well, we haven't used a Cl, so that must be in there. There's O3, 3 O's makes 2 O's, O2, so there must be an O in there, and then there's a dot, which is an unbonded electron. We've got to show that as well. Now, what actually happens then is that it reacts again. So if it reacts again, then what's actually going to be formed? So well, ClO dot is going to react again, ClO dot, with more ozone. So the depletion of the ozone layer is because the radicals keep reacting with ozone. So ClO dot will react with O3. The only thing it can make is O2, and we can have a look what's left over. So ClO dot that's made the radical reacts again with O3. Now, if it's making O2, look at this. O3, there's 4 O's on this side of the equation. 4 O's on this side of the equation, I can balance that up straight away by putting 2 in front of the O2. Now all the oxygens are accounted for and balanced. The only thing that's left then, I've not used a Cl, there it is, and I've not used a dot. And what I've actually done is I've made a catalyst, because the Cl dot rather, at the beginning of this equation has now reacted and reformed. So I've made a chlorine radical here. That unbonded electron makes it reactive, and so it's going to react again and deplete more and more and more ozone, and that's why there's a huge hole in the ozone layer. So any chemicals with Cl's in them, with a Cl in them, especially if the gases and can be released up into the upper atmosphere, are very, very dangerous. because they form radicals. Next question. The next question is hard because of the units, so you've got to know how to convert units. So a small amount of Freon, CF3Cl, with a mass of 1.78 times 10 to the minus 4 kilograms, so kilograms first of all is a problem to us, escaped from a refrigerator into a room of volume 100 meters cubed. Meters cubed is a tricky unit to deal with as well. Assuming the Freon is evenly distributed throughout the room, calculate the number of Freon molecules in a volume of 500 centimeters cubed. So look here, we've got kilograms. We're used to working in grams. We've got meters cubed. We're used to working in decimeter cubed. And we've got centimeter cubed. So we've got a mismatch between some of the units. Give your answer the appropriate number of significant figures. So we've got to work that out as well. And then we've got Avogadro's constant, 6.02 times 10 to the power of 23, a very large number. That's the number of particles that are in a mole of substance. So we've got a lot of numbers with difficult units to deal with. So how do we start off? What can we start off with? Well, what have we got? We've got a named molecule with a formula, CF3Cl, and we've got a mass. It's in kilograms, but we can convert that to grams if we want to. So we can times that by 1,000 and it'll come out in grams. I've got a mass in grams. I've got an MR. I can work out the MR of this. A carbon has got a mass of 12. A fluorine has got a mass of 19. And Cl has got a mass of 35.5. I've got an MR. I've got a mass in grams. I can work out number of moles of this. Numbers of moles. Moles is a good unit to work with. So let's do that first of all. So the MR of CF3Cl, when you work it out, a 12, 3 19s and a 35.5 is 104.5. I've got the MR of this. Now the mass of this, 1.78 times 10 to the minus 4 kilograms. There's 1,000 grams in a kilogram. So to convert that kilograms into grams, I multiply by 1,000. So that's my next step. I multiply by 1,000. 1.78 times 10 to the minus 4 times 1,000, 10 to the power 3. That's the number of grams. So moles equals the number of grams divided by the MR. Moles is mass divided by MR. So I've put the mass into grams by taking the kilograms and multiplying by 1,000. That's now the mass in grams. Moles is mass in grams divided by the MR that I've worked out, and it comes out as 1.70 times 10 to the minus 3. I've got the moles. Now that's your first step. If you see something with a formula and you've got a mass, it will want you to work out moles. That's always going to be the first step. Now they're a little way in, then we can carry on. So moles of Freon is that. I know that 1 mole of Freon, 1 mole of anything, the number of particles is that. I haven't got 1 mole of Freon, I've got 1.78 times 10 to the minus 3. But the number of moles that I have multiplied by Avogadro's number will tell me how many molecules or particles there are in there. So I've got that number of moles. I haven't got 1. 1 mole would be that amount, that number of molecules or particles. I've got that number of moles. So if I multiply that by by Avogadro's constant, it gives me this number. This number, 1.02 times 10 to the power 21, is the number of particles or molecules that I have in that number of moles, that number of kilograms of Freon. That's the number of particles or molecules that I have of Freon. Now, that escapes into 100 meters cubed. I want to know if I've got that number of particles in 100 meters cubed. If I took a sample of it, 500 centimeters cubed, how many particles would I have? Well, I need to do another little bit of maths, and I'm just going to do this to the side. 100 meters cubed. Well, a meter is 100 centimeters. If I had a cubic meter, a cube that was a meter by a meter by a meter, To do a cube, I take the height multiplied by the length and multiplied by the width. Now a metre is 100 centimetres cubed, so I've got 100 centimetres cubed height cube, 100 centimetres width cube, and 100 centimetres length cube. 100 times 100 by 100 is 1, 2, 3, 4, 5, 6. That's the number of centimetres cubed, a million, 1 times 10 to the power 6, 1 with 6 noughts. That is the number of centimetres cubed in a metre cubed. And it says I've got 100 metre cubed. So that's number of centimetre cubed in a metre cubed. I've got 100 metre cubed. So that is the number of centimetres cubed, 1 with 8 zeros, 1 times 10 to the power of 8. That's the number of centimetre cubed in 100 metre cubed. I have now got that in centimetre cubed. 100 metre cubed is 1 times 10 to the power of 8, 1 with 8 zeros, centimetre cubed. I only need 500 centimetre cubed, so I'm going to do a fraction. 500 divided by 1 times 10 to the power of 8 is 5 times 10 to the minus 6. That is how much I've got to scale down by. I've got to multiply this number to bring 100 meters cubed down to 500 centimeter cubed, because I know how many particles are in 100 meter cubed. I need to scale down to work out how many particles are only in 500 centimeter cube sample. So that's the number I'm scaling down by. So the number of molecules in 500 centimeter cubed is this number of particles that I had multiplied by my scaling down factor, 5 times 10 to the minus 6, and it comes out as 5.10 times 10 to the power of 15. How do I know about significant figures? What do I do? Well, when I'm looking at numbers here, I've got 1.78 times 10 to the minus 4. I forget about the 10 to the minus 4 when I'm looking at significant figures. I just look at this number here. Forget about the times 10 to the minus 4. 1.78. I've got 3 significant figures there, a 1, a 7 and an 8. 3 significant figures. 3 significant figures. Forget about the 10 times 10 to the power of 15. That's not important when we're looking at significant figures. 1, 2, 3. A 0 to the right of other numbers counts as a significant figure. If it's over to the right hand side here, it counts as a significant figure. 5, 1 and the 0 counts. 1, 2, 3 significant figures. 1, 2, 3 significant figures. That now matches.